Today's webinar is on reducing process heat with a focus on targeting, and we're going to be talking about some of the techniques of how to target energy use and heat recovery for your processes, and we'll get straight into it. So here's a bit of an overview of what we're going to discuss. I'll give a bit of context around energy use and continuous improvement for energy use, and then go into the basics of process heat integration. Then I'll talk about some of the terms that we use in this area and introduce the temperature enthalpy diagram to represent process heat transfer, which will then lead into composite curves and a bit of an example around that, as well as just some summary points in some upcoming webinars. So last time, way back in April, I presented a webinar about simple waste heat recovery projects, which basically applied a very simple methodology for looking at your process and trying to just locate waste heat that's being exhausted or put down the drain that you can simply just recover. It's a very basic level technique. Today's webinar is going to look at how we can get the next level of energy savings, and this requires a redesign, retrofit of the heat exchanger network. It's usually not as simple, although it also encompasses and will identify those simple waste heat recovery projects. So our focus is going to be on targeting for how much energy savings we can achieve in a redesign or a retrofit of a process heat exchanger network, or just of a new design greenfield site in the design of a heat exchanger network. So just a few, I guess, points on energy use and continuous improvement. So today we're starting at the top of this, I guess, cycle with doing some targets or benchmarks. This targeting and benchmarks is to essentially quantify your energy performance, compare it against perhaps what is the best technology available or the best that your particular technology is able to achieve. It's to set specific process targets and to apply some of these tools that we have in order to do that, such as pinch analysis, which is sort of today's focus, or process simulation. Then there's also other methods of doing it, such as process flow diagram reviews and plant walkthroughs. Some of these achieve lower levels of energy savings. They're a little bit tougher to apply to every project or every process. So we're going to focus mainly on the pinch analysis tool of doing targets for your process. Then these targets and analysis hopefully should lead to identifying projects. The project may be a retrofit of a heat exchanger network. This is where you might replace or add area to a heat exchanger. You might add a new heat exchanger. You may just repipe existing heat exchangers. Alternatively, or at the same time, you may identify a project that a process operations optimization that can occur, and that can also occur, be identified through this analysis we're going to present. And then thirdly, it may identify a project where you need to invest in new technology. From this preliminary sort of identification of projects, it leads to a more detailed evaluation. The detailed evaluation should include things like a detailed cost-benefit analysis, a potential utility modeling for predicting what will happen after you make a change to the process. This is particularly important for sites with cogeneration of heat and power. it may also include a process simulation of the changes in order to predict what the energy benefits are going to be, as opposed to just sort of an approximation. And then thirdly, it may include some sort of systems optimization where you change both the process operations and the set points of your operations and also the heat exchanger network. This hopefully leads to an implementation of solutions and the construction of an investment roadmap. And that may be a stage-wise roadmap of implementing sequential projects in order to improve energy. It may also include a strategy that your company may implement for energy and environmental goals. And then hopefully this leads on to continuing measurement and monitoring of performance. This is to confirm that energy has actually been saved and also to re-optimize your process system variables and to ensure that you achieve the greatest benefits. And so the cycle can continue to benchmarking and targeting and onwards. So why do projects that are today may be economic in the future? Perhaps they're not economic today, but 5 years down the track they may be economic. And this is a very useful graph of how projects can become economic in time. The black line here represents the cost index for capital costs, and the blue is natural gas cost index, and the coal is the red line. And you can see we've just sort of dotted what is going to happen in the future. You'd make a lot of money if you actually knew what that dotted line was. But nonetheless, if you look at the ratios between the two, you can see that back in 2002, which is the base year, the cost index ratio is essentially 1, where if you look at about the year 2010, you can see that for coal, compared to the capital index, it had doubled in its cost, whereas the capital goods had only gone up perhaps 10%. So this means that the payback that you would have received for a project back in 2002 is going to be a lot less now. So today's focus is going to essentially be around the benchmarking, the targets, and also the identification of projects. More so the targets today and how to do this. So what is the concept of process heat integration? Essentially back in the 1970s when we had the energy crisis, a lot of processes and plants and sites looked to reduce their energy consumption, especially in oil refineries. And so what grew out of this was the development of a number of systematic engineering methodologies in order to identify energy projects, process heat savings, and then to implement those projects. So process integration takes a very holistic systems type look at the process and sites in order to figure out how to better integrate and to maximize energy recovery and energy savings. These methods provide very valuable insight, and they help you understand how to combine within a process various heating and cooling demands, and also how to integrate heating and cooling demands between processes. In general, it answers two key questions. It answers what heat integration levels are thermodynamically and realistically achievable, very much specific to a process and a technology. And it also answers how can these targets be approached or even achieved for the particular situation. So why do we want to increase process heat integration? Well, simply it can lead to better process design. We save energy, we save cost, we save emissions, which is also saving costs with the ETS these days. We can have a better utilization of capital through reducing the number of heat exchanger units. We can also retrofit to increase production by freeing up capacity in the heat exchanger network, reducing its energy use, and then freeing up the amount of utility we have available, and therefore being able to increase the amount of production potentially. It can also help us save time in the process design and optimization phases due to the methodologies being very systematic and relatively easy to apply. So why do we want to set heat integration targets? Well, if we look at a site with lots of plants and lots of processes, then the problem of being able to decide how to integrate that can be extremely complex and very much a multi-dimensional optimization problem. So simply applying heuristics or applying experience can be difficult to know if you're even close to an optimum or whether you're in the ballpark of what is the economics. So targets help us to identify where there's inefficiencies in energy efficiency and also what is that potential. We tend to and it also helps us to sharpen our focus on which process is the least efficient in terms of comparing what its current energy use is to its potential energy use or much lower energy use. And a key point on this is the one with the greatest potential is not always the process that is the biggest energy user. These targets also help us to partition the complex problem into much simpler ones and make it easier to solve, and we'll sort of talk about how that's the case. So to introduce some of the basic concepts, we'll go back to the real basics and progress forward. So there's, I guess, three types of heat exchanger in general. There's a co-current, there's a counter-current, and there's cross-flow. In general, most of we try to put in mostly heat exchangers there in the counter-current flows. A good example of this is plate heat exchangers. Almost all plate heat exchangers are exclusively counter-current. Shell and tube heat exchangers, on the other hand, are a mix of counter-current and co-current, depending on the design of the shell and tube heat exchanger. For example, a U-tube shell and tube has one pass being counter-current and the second pass being co-current, or the reverse. Other heat exchangers are cross-flow, meaning the two streams or the two flows are perpendicular to each other. And each of these have their unique temperature versus length or temperature versus area profiles of how it changes over the length of the heat exchanger. We often call these, I guess, flows streams in the area of process integration. And so I'm going to refer to flows or mass flows as streams. There are two types of streams essentially. There's hot streams that are initially hot and require to be cooled down to some lower temperature, and then obviously cold streams are initially cold and need to be heated to a hotter temperature. And you can see on the two temperature enthalpy diagrams, if we have a horizontal line, then that essentially means we're changing in enthalpy without changing temperature. Therefore, it's condensation, or in the case of a cold stream, it's evaporation. The slope of the lines, if we have a sloped line, then we're having a change in temperature, which then releases a duty or gains in duty. And this slope of the line has some significance. If we look at the case of a heat exchanger or two heat exchangers on the temperature enthalpy diagram, we can see in this case we have a hot stream that's being cooled from around 100 degrees to 60 degrees and a cold stream going from 50 up to 80. The slope of these two lines represent the heat capacity flow rate. If we review our basic heat exchanger duty equation up the top there, with Q is equal to the mass flow times the specific heat capacity times the change in temperature. That mass flow times specific heat capacity is also called the heat capacity flow rate. And you'll notice that it has the units of kilowatts per degree C and is essentially the inverse of the slope of the lines that we see on the temperature enthalpy diagram. Another important point for these diagrams is at each side of a counter-current heat exchanger, we have approach temperatures. So on the left side of the first diagram on the left, we have an approach temperature of 10 degrees, and then on the right-hand side, we have an approach temperature of 20 degrees. What we call the approach temperature with the lower difference, we call it the minimum approach temperature. Essentially, as we shift these two curves together or apart, then that approach temperature can change as we try to increase the duty of the heat exchanger. On the right-hand side, we see another diagram with just a larger approach temperatures of 20 and 30 degrees, with the minimum being 20 degrees. So let's consider a very simple process. In this case, we've got a raw milk stream going into a separation process, and we've got skim milk going out the other side. For this purpose of the exercise, we're going to ignore the cream, which is which goes off and usually is cooled or has something else done to it. So if we look at the question here, it's how much heat can we recover in this process? So we can plot these two streams onto the temperature enthalpy diagram. If we plot them as shown, we can use a heater and a cooler to apply utility and achieve the various demands for utility for the two streams. Of course, this is very inefficient use of energy. If we were to take the cold stream and start to move it to the left-hand side of the diagram, we can start to show on the diagram how to recover heat. We can place a heat exchanger in the middle here between the two streams, and we can recover 2.6 megawatts of heat. At the two extremes of the hot and cold streams, we still need the heaters and the coolers. And you'll notice there I've identified that down the bottom of the heat recovery heat exchanger that there's an approach temperature of 10 degrees. That is also the minimum approach temperature. We often call this point the pinch, and we'll talk a little bit about why that's the case and what the use of that is. But nonetheless, we can say go to a lower delta T min. Instead of 10 degrees, we could choose 5 degrees. This increases our heat recovery, and what we're targeting for that heat recovery exchanger and subsequently also lowers our hot utility target and our cold utility target. We can look at this from the point of view also of changing what we select as our minimum approach temperature, or delta T min. If we were to start off at the extreme case of a minimum approach temperature of 25 degrees, then our heat recovery is about 1200 kilowatts. As we reduce our delta T min, our heat recovery increases, and subsequently our hot and cold utilities start to go down. In this particular case, we reach a maximum heat recovery and can't exceed this point at 3 degrees. And the simple reason for that is one stream is supplied at 10 degrees, has a target temperature of 10 degrees, and the other stream has a supply temperature of 7 degrees. And once you eliminate all the cooling needs, all the cold utility needs for the stream that's targeted to go to 10 degrees, there's no point in going any further. Okay, and so we essentially save hot utility and save cold utility, and we recover that heat. So how do we select this minimum approach temperature for a simple case? Well, one method of doing it is we look at the trade-off in an approximative way between energy and capital. And as we lower that delta T min, what we find is we get more energy savings. So if we look at this diagram here, energy cost is going down as we reduce delta T min. Conversely, we've got capital increasing, and it depends on as we go to a higher to a tighter and tighter approach temperature, then the amount of area we increases, and it increases at a faster rate because we have a diminishing returns law for duty. And so if we sum up the two, then we can essentially get some total cost curve, and from that select the minimum total cost, and that then should be used as our minimum approach temperature. An alternative way of doing it is to apply rules of thumb, and these rules of thumb are sort of presented here for various combinations of flows. In general, I think a liquid-to-liquid heat exchange in a plate heat exchanger, 5 degrees approach temperature is very common. If you're looking at a shell and tube, it tends to be a bit higher, between 10 and 15 degrees. And we've just had a comment here from one of the listeners that 3 degrees is common for a plate heat exchanger for liquid-to-liquid heat exchange. So that's obviously, you can see how that has somewhat changed over time with the energy to capital ratios. So what can we learn from this simple example? Well, first of all, we identified a pinch, which is the point of the minimum approach temperature. Above this point, we only used hot utility and the heat recovery, and below that point we used cooling. And what we find is a general rule of thumb is that we should only use hot utility above a pinch and only cold utility below a pinch. And we'll apply it to a bit more of a complex example in just a second. Then we have the heat recovery depends on our choice of minimum approach temperature, and we've explained how to try and go about selecting what that minimum approach temperature is. As we save energy by going to a lower delta T min, it is also useful to note that the amount of energy saved from the hot utility is equal to the amount of energy saved from the cold utility. So we've presented a very simple two-stream example, but the reality is in almost all industrial processes, you've got more than two streams, multiple hot, multiple cold streams. So how do we do this? And how do we target? So let's increase the complexity by 2. And let's look at 2 streams. So this is an example where we've plotted the temperature enthalpy diagram for 2 hot streams that are being cooled. The heat capacity flow rates are shown on the diagram, and you can see the handy dandy table at the top that explains the various supply and target temperatures along with the duties that are required to be extracted from these streams. We can go ahead and sum up within the temperature interval of 140 to 60 degrees what the total duty is that's required, and then put a diagonal line between these 2 points. So essentially what we're doing is we're compositing, or we're summing up between each of the intervals how much duty is required. And so what we can form are what we call composite curves, which is essentially a composite of all the process streams, of all the hot process streams in this case. We can also do the same process and method and apply it to cold streams, where we take 2 cold streams, we combine them together and in a similar method, and we come up with a cold composite curve. If we take this hot composite curve and cold composite curve and plot them on the same diagram and bring the 2 together, then we can form a pinch, or a location which we have dictated that we're going to not go below a minimum approach temperature of, in this case, 20 degrees. Now from this you can read off some key targets. In the center here, where we've got the hot composite curve of the process streams above the cold composite curve of the process streams, that region is our heat recovery target. Over to the right hand side is our hot utility target, and on the left hand side is our cold utility target. Now this is the pinch, and at this case it's about 90 degrees. Well, it sits between 80 and 100 degrees or thereabouts. And you'll notice again we're only needing hot utility above the pinch and only needing cold utility below the pinch. We can place in our heaters and coolers if we choose, just to re-illustrate that. Now if we want to increase our heat recovery, and it's a benefit to do that, then we can bring these 2 curves and make them come closer together. And in this case we've selected a delta T min of 10 degrees, and you can see that if we were to repeat this process and go to a delta T min of 5 degrees or even 1 degree, it gets closer and closer and closer. And of course the thermodynamic limit of an infinite area heat exchanger is a delta T min of 0, which of course isn't practical or possible. But nonetheless, what we see from this is the pinch temperature has also lowered, as well as the targets. And this is simply because this little kink in the cold composite curve is driving that pinch. And so it's just dropped a fraction. So the significance of this pinch, well, it's useful for a number of reasons. As you can see here, we can divide the problem into 2 distinct regions. Above the pinch, we've got heat recovery and hot utility use going on. Below the pinch, we've got heat recovery and cold utility use going on. So what we can say is above that pinch, there's a deficit of heat needing to be added to the system. And below the pinch, we have a surplus of heat. In other words, our process is trying to give off heat. Now, this leads us to the point of cross-pinch heat transfer. In this case, we have, if we were to have in our network, our existing network, a stream that is in the temperature range, a hot stream in the temperature range that is above the pinch, and it is exchanging heat with a stream whose temperature range is below the pinch, we call this cross-pinch heat transfer. Now, if you consider the situation where we've said that there's a deficit of heat above the pinch and there's a surplus of heat below the pinch, what we're doing is we're taking heat that is critical above the pinch and we're exchanging it with heat, and we're giving it to a location below the pinch that is a critical receiver of heat. And so the effect of doing this is we are increasing the duty of our hot utility use, essentially, and we'll increase the duty of our cold utility use. We're using more utility than is required or is predicted by our target. So bringing this back to the use of the target, we can come to a process that we already know its utility use. We know how much heat recovery that is already going on. We can take the hot streams, we can take the cold streams, we can apply this composite curve methodology, and we can pinch the two curves together. From this, we can read off our targets and compare our target to the network. And in this case, we can figure out if we're not meeting the target, then we can look for areas of cross-pinch heat transfer. And essentially, one simple methodology to retrofit the network is to break the links, in theory, of the cross-pinch heat transfer, and then to look for reintegration of those points within the heat exchanger network. This may require a new heat exchanger, it may require repiping, just depends on the situation. We're going to discuss how to do retrofit and a methodology around that in a future webinar, and I think it's on the 16th of November. Now, the methodology that we've presented so far is fine for a single process. It's fine if we're able to take all of these hot streams and directly integrate them and exchange heat with these cold streams. But if you consider a large site, here's a dairy factory, and each of these blocks representing different plants on a dairy factory, a cheese plant, a powder plant, MPC plant, cream plant, casein plant. And there's many other plants that you could put on there, such as the milk treatment plant, and depending on what site you're at or what particular processes you have on your site. And it's not necessarily practical and smart to assume that you can exchange heat from your cheese plant with a stream in the cream plant, because there's distance, there's temperature loss, there's lots of capital cost involved with piping to those plants and back. There may also be good product quality and hygiene reasons why you don't necessarily want to have long pipes. And so the application of this direct integration has to be used wisely. And so there are methodologies around site-wide integration and a strategy to do with that. And so in this case, some key points for this is we tend to prioritize process-to-process heat recovery within a plant. Another reason why we do this is, especially in New Zealand, is a lot of our operations are semi-continuous. They require cleaning and they tend to be stop-start. And so there is a timing issue between when heat is available and when sinks of that heat, what needs heat, is also available, and they may not coincide. And so if we tend to focus on defined plants or zones where we use our engineering judgment to decide that these streams can be directly integrated and do tend to occur at the same time, then we prioritize heat recovery within those defined little zones. We then can target the utility use for those zones. Now, I didn't talk about this today, but we can also apply this technique to look at what levels of utility we require for those, I guess, process units. Then we can look at, once we analyze and look at the retrofits for each of the individual little plants, we can look at doing heat recovery via the utility system. A very common example of this is in the oil refineries, where they commonly are able to have, some plants have excess low pressure steam, while other plants are in deficit of low pressure steam. And so a method for integrating across the site is to use the utility system, where one plant generates LP steam, feeds it into the steam main, and then at plant B, at another plant, they take the LP steam off the steam main, which is circulating around the whole site, and therefore are able to be integrated indirectly through that utility system. So once we've analyzed these individual processes and have their utilities, we can start to look at how these utilities are able to recover heat within the utility system. It's also useful for being able to decide the utility temperatures and what you should select. And so you can then select these and decide or figure out how much heat recovery that can go on. Okay, so let's just sum up what we've learned today. I know I've gone perhaps a little bit too fast, but I'm going to stay on the line to answer any questions you have. It's a little bit of a heavy load, I think, in terms of perhaps technical today. So just to sum up, energy use is part of a whole continuous improvement plan and strategy. And the capital and the energy costs are changing over time. And so we should consider this as part of our strategy. Pinch analysis and process integration techniques are extremely useful for being able to target heat recovery in the utilities system, and we can do it very much specific to what process you have on the ground. It's not just specific to the best technology that's out there, although you may want to consider if it's economic to move towards a better technology for the process. In the ideal scenario, we should limit and eliminate, if possible, any cross-pinch heat transfer that occurs. If you don't do this, then if you follow the minimum approach temperature rule and you strictly follow it, then you are thermodynamically impossible to meet that target, and you have to increase the amount of utility use that you use. And then finally, site-wide heat integration targets can be useful for summing up the targets of individual processes, and then use the common utility system in order to recover heat. So just some useful references. There's a couple of very good publications back in the early 2000s, also in 1998, and these are given at below. If you just search the web for the titles of these publications, you'll be able to find these techniques in those publications. They also have several real-world and examples of how to apply the method and some methodology around the integration and its benefits. So just looking at what's coming up, we have James, Dr. Neil is back on in a couple of weeks talking about fan systems and control, and then you can look through there at the other webinars that will be coming up. Just a plug for the next process heat one on the 16th of November. We're going to take the techniques that we've learnt today and we're going to apply it to retrofit situations. Now that we've introduced the techniques, it's going to, I'll take some real-world examples of existing heat exchanger networks and look at how we can retrofit those networks in order to save energy utilizing our targets. There's also, if you're interested in past webinars, click on the link there in YouTube, EcoBusiness, some useful videos from the past, and also if you want to review today's webinar and re-listen to it, re-look at it, then you're welcome to do that as well. And just a reminder of the EcoBusiness program, and if you have any questions, you can seek advice from your Eco account manager or via the website. And if you have any questions, you're also welcome to email us here at the Energy Research Group. Thank you for listening to today's webinar. I'll stay on the line a little bit longer and answer any questions. Now we've got a question here from John about the capital cost trade-off and energy capital trade-off. So I'm just going to flick back to that slide and just sort of talk a little bit more about it. The question that John has is there a version of this graph that is based on net present value? And that's a very good question, John. One of the methods for constructing this graph is to do a type of net present value that's based on life cycle cost, or another way of putting it is a annualized cost. In this case, you can take the time value for money of the capital, as well as you can look at how energy cost is likely to increase over time, and so you can go ahead and adjust what your prediction is of the energy savings over time, and therefore work out a bit of an annualized cost for that energy in the capital, and then do a very similar graph to any other graph on that, using that same sort of plot. Okay, we also have, John also asked about some real-world worked examples. Yes, we're going to be doing that next time using a retrofit. Today was more of a introduction to targeting and to get you introduced to the basic concepts so you're prepared for how to take a real heat exchanger network, do some targeting, and then decide on some retrofit options. And then we've just got a final question here from David around, is this methodology applicable to small plants that don't have heat exchangers? Well, generally, no. It's not really that applicable. It's essentially, if there are, if your plant has heating needs and cooling needs, that is, I guess, can be non-electrical, then yes, you tend to have heat exchangers as a result of that. So it's less applicable to plants or processes that don't require heat exchange or hot or cold utility. Another question here from Gilbert. does this mean the break-even point is where the energy savings and capital cross? Okay, the answer is no. The answer is no to that. The break-even point can be actually at a much higher delta T min. It can be economic to do it at a much higher delta T min, but what the minimum point of the total cost curve tells us is the most economic, the point where you maximize your economic benefits. The cross, and this does not, very rarely does it actually line up with that crossover point of energy and capital. Just depends on your process. Now I've got a few more questions coming through here. Okay, does the use of delta T min not produce conservative surface areas than using log mean temperature difference? Okay, this concept of the minimum approach temperature shouldn't be confused with heat exchanger sizing methods. In this case, what we're doing is we're applying a very simple test and measure in order to adjust what levels of heat recovery we get in order to do a rough optimization of cost. From that point, we can then go to designing the network and sizing the duties of each of the heat exchangers. In this case, we would take an approach such as the log mean temperature difference. Or another approach is the effectiveness NTU method for sizing heat exchangers. Next year, we're going to look at holding some webinars that are specific to sizing and rating heat exchangers and also monitoring heat exchangers for fouling in order to detect when we should start to clean our heat exchangers. Okay, lastly, another question from Ash has asked, is there some quick software to help with this? Yes, there is software available, freeware. If you want to get in contact with us, we'll be able to send you that software. It's a simple Excel spreadsheet that you can do your targeting on and look at using it. There's also lots of commercial software out there that does a lot more fancy things like automated network design and automated network retrofits, but of course you have to look at the cost-benefit analysis. The other method is, of course, now that you've got this basic level of understanding, you can also engage in professionals who work in the space of process integration full-time. There's a number of companies out there that can do this high-level analysis and try and figure out where you can save energy for your process. So it just depends on what situation you're in and what you hope to achieve as an engineer or as a company. All right, send through any more questions that you have. Happy to answer any more questions. Well, it doesn't look like there's any more questions, so thank you for coming to today's webinar, and please join us again in 2 weeks, and goodbye.